everybody. We've got a small number of people here. We've got some more on Zoom, which is good. And this is our first attempt at doing this, so I'm glad there aren't too many people, because if it all goes horribly wrong, it won't affect quite so many. The reason I'm doing this meeting today, although I have actually given this talk once before, is that we were anxious to get 2 meetings in this year, and at short notice, I was the only person I could find. So this is why I'm doing it. It's a slightly shortened version of what I gave to the Computer Conservation Society a while ago. Some slides will contain information I won't talk about much, and the reason for that is simply that I'm used to giving things to students, and students don't buy books, and so you have to put everything on the slides, and you're not going to talk about it. So that's it. I'll put the slides on the website afterwards. You'll see about the website later on, and a version of the video, which will be okay. And you may be asking, first of all, why someone who isn't from Edinburgh University is talking about this. Well, the answer is that I probably got to know more about the system overall than anybody else, although in not so much depth, because I was the sole system support at Kent when we were running this system. So that's why. So, oh, it's all right, we're on the wrong screen. So some basic information first of all about what this system was. It was as it says here, this is almost like a sales brochure, an efficient multi-access system, which was offered interactive and batch facilities, which sounds obvious, but it wasn't obvious at the time, on ICL mainframes and IBM mainframes. And more about that later. When do they run it? Well, they ran it from 1970 until 1992 at Edinburgh, which is a very long time. And the predecessor and the development phase happened between 66 and 70, when it wasn't even ICL, it was English Electric. Where mostly the University of Edinburgh, but between 78 and 86, it ran at the University of Kent, and I looked after it. It was developed at the University of Edinburgh, obviously. It was a sort of joint effort between the Department of Computer Science and Edinburgh Regional Computing Centre, which got formed somewhere along the way. And I did work at Kent to make some changes to it as well. So, 1966 started, and this bit of the history is quite short, and I'll whiz through it. It saw the foundation of the Edinburgh Regional Computing Centre, and they had a KDF9, which was English Electric, and it supported a language called Atlas Autocode. A lot of people think autocodes are actually assembly language, but they're not always, basically any programming language got called an autocode, at least some of them did. Atlas Autocode was a high-level language, a sort of level of Algol, probably a bit higher level than C. And in the same year, they put up a team to try to get multi-access. This machine did not have, or the machine they were going to get, the KDF9 was temporary. The machine they were going to get was an English Electric Leo Marconi System 475, which is basically a sort of clone of an IBM mainframe, the IBM 360 at the time. And it was the most powerful system in their range, and it only supported batch. So, you punch these things on cards or paper tape or whatever, and you've got printout. The guy who led it was somebody called Harry Whitfield. But the model of the whole team was an ICL project team, or English Electric in those days. This was not a good thing. ICL project teams later on turned out to be quite bad for us. And the most recent one, of course, was the ICL, I forgot what they called it, but they started this project called Horizon, and we know where that went. So that's also so it had managers, team leaders, designers, 25 programmers, technical and coordinating committees, and you can sort of see where that was going. It wasn't, basically. But they developed a language called IMP, and that was really the Edinburgh part. They had compiler people, and the implementation language they used was going to be IMP. Quite unusual in those days to use a high-level language for developing an operating system. And it's very similar to Atlas Autocode, with one or two of the difficult bits taken out. They eventually got their system 475 2 years later in two pieces. The disk drives didn't arrive till 69. And they took the KDF9 out after that, and they just run batch. And the EMAP, as it was called, the project, didn't go very well. And by 1970, they basically said, let's just disband this team, we're not getting anywhere. They weren't getting a good product. So then somebody said, well, let's try and do it just in the university. And they had a team of about between 3 and 7 people, which turned out to be plenty. And they obviously were not quite as rigorous as the ICL people might have liked, but they got it going pretty quickly, within a year. And they had a pilot service, and they called that EMAS, the Edinburgh Multi-Access System. And it quickly became overloaded, and they went and got another 475, in fact. Got the money for that, and got 2 of them. So that was good. But it was still overloaded, and eventually they wanted to get a replacement hardware. And the obvious thing would have been, because the English Electric thing was really not going anywhere, would be to get an IBM mainframe, because that was compatible in most of its hardware with the English Electric. But there were politics involved, and the politics said basically you've got to buy a British machine, so it's going to be an ICL new range machine, which they were still designing. Something called a 2980, which was the most powerful one they had. And it had to be running the ICL operating system called VMEB, which stands for Virtual Machine Environment, and there's lots of arguments about what the B stands for. Well, the 2980 was delayed by a year. It was an incredibly complex machine, and it wasn't microcoded, it was all hardwired logic. So ICL said, well, what we can provide you with is a 2970, which is a much smaller machine, about 30% of the power. But the thing about the 2970 was it was microcoded, so they could get it developed more quickly. It only had 1 megabyte of memory. I think the VMEB one was going to 2980 was going to have 2. And that supported a batch system, did VMEB, and it also supported interactive use, 2 users. That's all it could do. So it was pretty bad, really. And I still said, oh, we'll fix that, we'll fix that. So the EMAS team said, look, can we get EMAS going on the 2970? But instead of using big terminal multiplexers, let's try and put it on our network. And they decided to use a PDP-11, and I'm not going to talk about PDP-11s today, but 16-bit mini computer as a front end to the rest of the network. And it turned out that 2900 is actually very, very well suited to high-level languages. It's a lovely architecture for high-level languages, such as IMP. So you've got your operating system largely written in IMP. There's only a very small amount in assembler, and all you have to do is change the way you do input-output. And better than IBM architecture in that sense. So they did it. They actually got EMAS running pretty quickly, actually, on a 2970. And they wrote a paper about it. And the most famous paper, more than one, is an experiment in doing it again, but very well this time. And I've got a link to that on the support website. They had a pilot service, and it supported 30 terminals plus batch. So it was a lot better than anything they'd had before. And a full service was offered on that from October 78. Now, the interesting thing about this, as we'll see, is that the University of Kent decided to go with this. We were having real problems. We were running a system called VMEK. VMEK was written in a hurry to basically provide a way of running ICL software on small machines. The 2960 was only 30% of the power of a 2970, so 9% of the 29 10% of a 2980, and it had 1 megabyte of memory. But then we managed to get 2, and we were running VMEK, and we were running a 13-week rolling average of our reliability, of what the MTBF was of the entire system, and it was 20 hours. So after 20 hours, you could pretty well guarantee you'd had a crash. Might be hardware, might be software. And it was not reliable. I was actually employed at one point as a part-time programmer, and my job was to do testing on it. And I submitted in 1 month 200 bug reports. And I'm sure they had an effigy of me in Bracknell, which they stuck pins in. So there we are. So it worked, you know, and we got EMAS in. I was deputed to take the guy to dinner down at what is now Wetherspoons in Canterbury. And, before that, we installed it. It took about an hour and a half to install it and test it. It was just that simple, and it worked. By October 78, the 2980 had failed to meet its benchmark, and they've got a bit more reliability, but not much. And they decided to run it for regional service. More about the Kent bit in a minute. And a year later, they said, this 2980 is useless. We can't support a regional service. This is Glasgow, Strathclyde, Edinburgh, all in one place. And eventually, they managed to get the computer board, who provided the money, to get EMAS, to let them switch it to EMAS. And they did that in January 1980, 2 weeks after we had switched to EMAS. And over the various next few years, ICL kept providing upgrades. This is because ICL were finding it expensive to maintain. The 2980 was a very complex machine, as I said. ICL had decided they would go for rather better medium to large-scale integration of chips to build new generations of the machine. And they did that by entering into an agreement with, guess who? Fujitsu. And Fujitsu were making the chips. So that was the start of the marriage between Fujitsu and ICL. And those upgrades were okay up to a point, but eventually ICL were clearly in financial difficulties. They weren't producing anything new, and it was expensive. And they managed somehow, I don't know how they did this, they got an Amdahl 470V7, which is basically another clone of an IBM mainframe. And of course, they still had the expertise and the code to put EMAS on that. So it's relatively easy to take it back from the ICL architecture onto an IBM architecture. And they were running a re-implemented EMAS known as EMAS 3. And that ran for several years. I was involved a bit in EMAS 3 as well. So by mid-1988, they moved it to something else. I've put different manufacturers here because it depends exactly when you look. ITEL, NAS, National something systems, and Hitachi. And it is an ASBL80, a massive machine. I think it has 16 CPUs with 8 front-end PDP-11s. It was an absolutely enormous system. And they ran that for 4 years, and by that time the PC was taking over. And so they finally shut it down in June 1992. And I've got a little account actually from somebody who was one of the first users of EMAS when they were trying it out back in 1970, and was one of the last people there when they shut it off. He was doing research on it the whole time, which is rather nice. So here's the timeline, just to sort of firm it up. The EMAP project, the green, started in 66 and ran up to 70. EMAS 1 ran from obviously around the same end of that to development up to 71, and then EMAS 2 came along in, they called that retrospectively, in 76 onwards, and then eventually EMAS 3 in the mid-80s. So it was pretty good, really. So it spanned 26 years altogether, and the service for users spanned 22 years. Not a bad lifetime for a single operating system developed by half a dozen people. And our service at Kent spanned 7 years because we wanted to run actually an Amdahl or an IBM afterwards and carry on running EMAS. And we went through quite a lot of that. I actually developed EMAS 3 on the IBM machines that we were going to use. I spent a lot of time at IBM. And then the salespeople, it was the first big sales thing they'd actually worked on. Totally screwed it up, basically. And we didn't get it. So we got a VAX cluster instead. We couldn't have a single VAX because none of them were powerful enough. So they gave us 2 little ones as well, which was pretty useless. So apart from EMAP, it was a very small team, probably half a dozen people. None of them knew about all of the system. If any of you have ever read, and this is rather pushing it, Harry Harrison's Death World 2, which is about the scientists not talking to each other and therefore not knowing how things worked. For example, they worked out a way of communicating with each other so that A was a single beep, B was 2 beeps, C was 3 beeps, and Z was 26 beeps. They never talked to mathematicians about any other way of doing it. And this is the same kind of thing. A lot of the EMAS team didn't talk to other people, and they didn't talk to each other. They were just too deep in what they were doing. And I used to visit Edinburgh, and I just make some triggering comment, and they go, "Oh, can you do that?" You know, and then we'd get something happening. So it's quite interesting. So then let's move on to the next phase, which is the University of Kent, and we ran the Kent Online System service on the COS on an Elliott 4130, a little 24-bit machine with 64 kilowords of memory, and then we built some bootleg memory as well. We have a second one later on. It's essentially BASIC. We ran on that for teaching and a couple of other things, and a substantial batch service. And that was the university mainframe for 10 years. And we wanted really to get a PDP-10 or DEC System 10. And that was the plan for 1976. All the other universities bidding at that time got DEC System 10s. But we just hit at the wrong political time. There's no, you've got to buy British. So we got an ICL machine. And as I said, the MTBF was about 20 hours. They would send out fixes to us. They were badly Xeroxed hexadecimal patches that you had to type in on cards and then feed into the system. And there were no checksums. So it was absolutely awful. It wasn't very user-friendly. I'll give you an example. If you wanted to copy a file from one place to another, you had to type in quite a long thing describing exactly where the original file was that you wanted to copy. Then another one saying exactly what kind of file you wanted and whereabouts in the system to put it, what the block size you wanted was and everything else. Then a third command to actually copy the file. And I ended up writing a file copying program in short order for that. And we ran that for a while, and about, it must have been something like early 78. ICL said, it's all right, we're going to fix VMEK, we're going to re-engineer it, we're going to rewrite it basically. And we thought, and then they said, the only thing is we're going to slim it down a bit. And slimming down to them meant taking out a lot of the management facilities, which were essentially if you were running a university service. We could not use the new VMEK, it would have been impossible. So we were definitely very worried. And so we investigated alternatives, and our deputy director at the time, Mike Garside, decided to get hold of Edinburgh and ask them to send someone down. So in April 78, a guy called Peter Stevens from Edinburgh installed EMAS one evening. As I said, in time for dinner, we went down to the town on the bus and we got a nice meal. And I got to know Peter very well. He was a lovely man. And he was reputed to be hard to get on with. I never found that. I know people who did find him hard to get on with, and usually it was because they were trying to big themselves up and look clever. I just found that that's where I learned, if you don't know, ask, which is what I was doing this evening when I didn't know who somebody was. And I did the sole systems stuff for EMAS, the actual operating system. We had other people doing networking. Somebody else did the PDP-11 software, which was different for us because we had different network. And just to give you an example of the sort of thing we had, we tested things, and I'll talk about the EMAS director later. Early testing showed there was a lockup in that when we ran some tests with lots of users. And it turned out that if you didn't have too many users registered on the system, not the number of people using it, if you didn't have the right number of people, if you had too many people registered, it would eventually lock up. I found that within about 3 or 4 hours of poring over the source code. And just as I'd finished poring over it, the guy who'd written it phoned up and excited to say, "I fixed it." I said, "I know, it's this, isn't it?" He said, "Yeah." So I was quite pleased with that. It was quite early days as well. So inexplicably, this system did not go as well as we thought it should. Okay, we got a very weak machine, but it turned out that ICL had this range of machines. At that time, only just three: the 2960, the 70, and the 80. And all of them were incompatible. It was supposed to be a range. At the user level, they were compatible, but the way you controlled the hardware and controlled various features of it were different. And for those of you who know about these things, what happened was the translation look-aside buffers were turned off. Don't know what those are, don't worry. We found that was because the bit that controlled those was different on the 2960. So I went up to the operator console and typed this incredibly dangerous command and actually flipped the bit, and it all sprang to life. So that was good. And so that was really good. The other problem we had was rather interesting. It was the PDP-1134, which was in the machine room with the 2960, was actually connected to it with a big thick cable, and we were getting parity errors, i.e. errors on the link between the two, and we couldn't work out why. Turned out that there was a power feed at one end of the room for the 2960, and a power feed at the other end of the room for the 4130, which had been there. And that's where the PDP-11 was plugged in. And there was an earthing problem between the two. So we got a nice thick bit of copper braid and joined the two together, and it was fine after that. So yes, sometimes you have to do these things. Our Kent network wasn't based on anything to do with the Edinburgh one. It was a Cambridge ring. And all we had to do was change one module inside the front end, the PDP-11, and it worked. And every day between 4 and 6, we would run trials, and it worked really well. The changeover took place after the end of our term in December 79, and it was a once and for all change. And one of my colleagues wrote a utility to transfer all the files by reading the VMEK disks and writing stuff to EMAS. And it worked just like that. What we hadn't realized, and I didn't realize until fairly recently, was that we changed over in December 79 and started using EMAS in earnest. Edinburgh had only started using it in earnest 2 months earlier. I hadn't realized we were so leading edge as that, or bleeding edge. The MTBF was much better. It went from 20 hours to 2,000 hours, would you believe? And that's partly because EMAS was very reliable. In fact, it was incredibly rare to have a software crash. But also because when there was a hardware fault, EMAS could largely fix those without even thinking about it. What EMAS did was, for example, a good example of how bad VMBK was. The memory system on the 2960 used Hamming correction codes, which basically means that if you have a single bit in error in the memory, the hardware will detect that and correct it for you automatically, but tell you that it's had to correct it. If there are 2 bits in error, then it has to just crash. Can't do anything else. And what VMEK did when notified of a single bit error was it said, oh, it's been an error. Let me just clear that. Okay, clear the error, and we'll carry on. Didn't record it in any way. So of course, after a while, something else failed in the same piece of memory, the same chip, and it all went. What EMAS did was log the fact that there was a single bit error. Once they print out a report showing you which chip you had to change on which board. And so that was a lot better. And we went up to 2,000 hours. Our ICL engineers were a bit of a mixture. One of them was an incredibly nice guy called Harry, who actually did believe us and all the rest of it. But we had 1 or 2 others. We had one who was actually a former Kent student, very much a company man, and he distrusted us all the time. And there's a story about the printer where one day the EMAS put up a message. I don't think I've actually got this on the slides. He put up a message saying that the hammer driver fuse was blown in the printer, and we told him, and he said, "There isn't a hammer driver fuse." No. Wouldn't believe us, and eventually stalked off to his office, looked at his manuals, and came back bearing a fuse. Opened a small flap he didn't even know about beforehand, and put the fuse in, and it worked. And that was the sort of thing we had. 1982, we did have a serious problem. EMAS kept crashing. Turned out it wasn't EMAS that was crashing. It was the hardware. The hardware was saying, something's gone terribly wrong, and we're halting the microcode now. And we went, huh? and it used to happen several times a day, and then it wouldn't happen for 2 weeks, and then it would happen again. And eventually I said, right, okay, I'm going to have to look at this. Next time it crashed, I had a look, and I took the machine for about 2 hours, and I discovered that it was always the same user who was causing the crash. It wasn't always a physics postgrad, it's always a physics postgrad. And it turned out that he was running a Fortran program that was overstepping an array, and he was overwriting something called a descriptor in memory. And there's hardware to detect illegal descriptors. That hardware had a design flaw in it. The design flaw meant that one particular bad descriptor wasn't detected by the hardware, and it was handed back to the microcode, which then said, right, we'll just use this value then. And it was a this can never happen piece, so the microcode halted. So we had to do something about that. And I ended up, the engineers by this time were very cooperative, and they gave me a microcode training manual, and I got a microfiche reader, and I sat there for quite a time actually, looking through the microcode and eventually finding out how to patch it so that it would actually throw up a totally new kind of error, which EMAS could then deal with. Then I had to modify EMAS in 3 different levels, and it worked. Now, you'll see more about this later on, but the structure of a 2900 at that time was rather weird. It had something called an OCP, which we would now call a CPU. No memory, just the actual sort of bit that does the churning. And we acquired a second one from the 1981 census. I remember going up to Southall on the train and inspecting it with one of our engineers, and then coming back and saying, right, yes. And we had to pay £350 to have it shipped down. ICL gave us some cables and things, and we added some more memory, and it worked straight away, which was quite nice. The only problem was, if one of the OCPs wanted to stop or pause the other one, it couldn't do it. It didn't work. Guess what? Incompatibility in the ranges. 2980, the 2970, the 2960, all did it different ways. So back to the microcode, a bit of a read. I produced actually what was I think a half sheet of A4 with all the definitions of what I had to do, modify the system, and it just worked. And then we ran it pretty well error-free until 1986 when we shut it down. And I still have the board I stole out of the OCP that day. So we contributed various things, printer accounting, applications, basic. We had an assembler which had come from VMEK, and I wrote a sort of wrapper for it to allow us to run it on EMAS. BCPL, which I wrote as a compiler, quite a lot of packages, a different editor, and so on. For those of you who know Unix history, one of the editors was something called Ed, and we were using that on VMEK because the VMEK editor was so terrible. So that's about 1981. We were running EMAS. That's EMAS on the operator console right in the middle. And you can see also, but the cabinet at the back left, I don't think I've got, no, I'll just go back again. Can I go back? Yes, I'll leave it. So moving on, yes, you can have a look at that in more detail later. Implementation-wise, this is what I'm going to talk about now, which is more technical. The 475 version, I never really saw the source code for, because by the time I got there, it had been gone for several years. The IBM and AMDAL and NAS one, EMAS 3, was based on EMAS 2900, and I do have some of the source code, but not all of it, because I only worked on part of it. The 2900 sources, I have nearly everything in terms of the system source code for the 2900. Apart from a couple of pieces. And what you see now is a combination of things. It's the papers and manuals that I have read, talking to people on the project, I shouldn't forget that, and reading the source code. I really know the source code very well. I had a big box on the floor with all the source code in it at the time. So the first thing to say about EMAS is it's really weird when it comes to files and paging. Anybody know how Multics used to deal with files? I don't suppose anyone does, but okay. So what happens here is that you don't open a file in the same way you would on, say, Unix or Windows or anything else. you don't say, I want to open this file, and you get given a magic number back that you use to access the file. Well, you do, you get given a number back, but what the number is just actually an address in memory. You connect them into the virtual memory of your process. So once you've connected a file, you can access memory at that address. And if the address you're given back is actually the address of the first byte of the file, and the next one is the second byte, and so on. So basically, your file appears as an array in memory. Of course, it's not actually in memory at that point. All we've done is make arrangements for it to be brought in as required. So you don't have any kind of read system call to read a file, if you don't need one, or write or seek. You just go to whichever place in memory that part of the file is and read and write the memory. It just works. Files are divided into what they call pages of fixed size, 4K actually. And a page of a file is only brought into memory when it's referenced. It might be referenced because you want to read and write the file, but this also applies to programs as well. To load a program, slightly simplistically, but to load a program, all you do is connect its executable file in virtual memory and jump into it. That's it. When you disconnect the file, when the memory is needed for something else, whatever's in that piece of virtual memory gets written back to the disk. And you can share files between processes simply by having them connected in two different virtual machines at the same time. So you automatically share code. And if a file is being used by multiple people, only one copy of that is kept in memory as well. So it's very efficient. And this is this doesn't tell you very much, this picture, but this picture is obligatory. It's one of the rules that if you talk about EMAS at all, you have to actually show this picture. Right? So it's here. And it's basically a user is accessing some file here, and part of the file is mapped onto the disk somewhere, and the same for another file there. I'll go on to the system kernel now, the most important part of the operating system. Relatively small, as kernels should be, not like Linux. And the system uses a very small message passing kernel. Messages are a way of passing away a thing between parts of the kernel. You fire a message to a different part. So if you want to read something from the disk, you fire something at the disk driver, and the file system might do that. Messages are always 32 bytes in EMAS, allocated from a pool of memory, basically. 4 bytes to the source, which is a magic number that tells you which part of the system it came from. 4 bytes destination, which is a magic thing that tells you where it's going, and a payload of 24 bytes. Why 32 bytes? Well, they were being really clever, and they had a way of passing stuff around using the floating point registers, which turned out to be 32 bytes. That's why. It's the only reason. And a lot of the processes are built into the system, what are called non-page processes. In other words, they're actually resident in the machine's memory the whole time. The device drivers, as you might expect, the paging manager, the implementation of semaphores, which are a way of locking different parts of the system while you're doing things. Something called the active memory handler, which I won't go into too much. The scheduler, which decides obviously how resources are handed out. An interval timer and real-time clock handler. A configuration controller. One of the things you could do with EMAS was you could say, "Oh, I've got a second OCP here. I think I'll bring it in now." And then later on, you could say, "Let's take one OCP out of the configuration. Let's take 2 megabytes out. Let's take a disk drive out. Let's take an operator console out, and let's boot another machine completely separately for testing." And you could do that on the fly without stopping the system. And something called a bulk storage mover, which actually got used a lot. And it essentially moves stuff around on different forms of storage. Anybody knows about the Unix DD command? It's a bit like that, but it's built into the system. And then this part of the system, the kernel, is actually known not as the kernel in EMAS, it's known as the global controller. And there's more than one instance of it. If you have 2 OCPs, then there are 2 instances of the global controller, and they work separately, but they communicate. Right, now let's move on to the process, and I've got a diagram in a minute to firm all this up. Every non-resident process in the system, in other words, a user process, you, or something that's doing something for the system that's important, includes an instance inside it of what's called the local controller, and I'll talk more about that soon. Local controller is actually a resident part, and it shares code and it's privileged. So it's really part of the system. Each process has its own local controller, but obviously the data and stack are different for each process because it's a different program. And each non-resident process, i.e. ordinary process, has a privileged portion supplied by something called the director. And again, the diagram will make this clearer. And you've got share code, and then you've got per process code and data. And then lastly, you've got the non-privileged part of each process, totally non-privileged, and you can do what you like in there. You provide something called a base file, and the base file can contain whatever code you like, and it's all paged. It's connected to virtual memory, and in practice, there are very few different base files. The main one was the Edinburgh subsystem base file, and that's a normal user interface. When you log in, you'll see in the Edinburgh subsystem. But you could supply your own if required, and some brave people did. And there were special base files. We had something called the scientific jobber, which was invented by Edinburgh way back, as a way of getting batch to go faster for small student programs. You know, you've got a student writing their first Fortran program of a dozen lines. You don't want to spend all that time loading up a compiler, doing all the stuff you have to do, and then running the program. The scientific jobber had a resident compiler and could do it very fast. So the processes in the system which were paged, there were some system ones, and there were 5 that were permanently running. So as soon as you start the system up, these 5 will pop into view. Something called direct, which had operator control. You talk to it at the operator console. It handled all the logon and starting a process. Volumes, and they all had to be 6 characters, you see. Tape administration, did backup, archive, asking the operators to put the tapes up and so on. Spooler, which was input and output spooling. Much more complex than you think because they had lots of remote printers, remote card readers, even remote paper tape readers, card punches, you name it. Then later on we had FTrans because we got into the academic network, Janet, Joint Academic Network in the UK, and they were into a whole series of OSI protocols, one of which was Blue Book for file transfer. That all got thrown away when the internet stuff really came through. And electronic mail, which was called Grey Book. There were loads of other colours too. Red Book was remote jobs and so on. And all of these had their own specialised base file to do whatever they had to do, apart from direct, which for reasons we'll see had none at all. Now, local control, this is a really interesting thing. This is what made EMAS quite efficient and also quite nice to use. It's part of each page process, and it handles, among other things, the strategy for paging. The global controller is responsible for the paging mechanism. So the actual action of moving pages in and out of memory, because that's what happens, of course, all the time, the strategy, which page to move, is up to the local controller. The local controller is told, you have this many pages you're allowed to have in memory at once, and you can't exceed that. So it's the local controller that decides what's going to happen. And the local controller has to enforce that. Because it's a privileged piece of code, it can do that. Thrashing, for those of you who don't know, thrashing is the problem when you get too big a program trying to use too little memory, and you spend all your time accessing the disk, trying to move stuff back and forth. So you don't really get that in EMAS in the same way, because any process can only thrash against itself, because it's only given a certain allocation. It's somebody else's problem. And if that happens and the process is detected to thrash, it is slowed down. And it says, okay, well, you're not going to run so often, but you can, when you do run, you can have more pages. And that, of course, gets the system back under control, so it doesn't affect the rest of the system. And that algorithm for doing that is driven by a table, so you can change it if you needed to. And batch processes use a completely different table. In a batch process, you don't care if the response time is terrible. If the batch process says, do this, and it takes 20 seconds, so what? Nobody's watching. If somebody types something that takes 20 seconds, they get really annoyed. So you get a different profile for the two. And actually, their research showed that there's an optimal time for for sort of delays in response to typing a command. If you type a command and you get really fast response, that's fine. If you type a command and you get a slow response, but not that slow, like a second or two, that's really, really bad, because it really upsets people, because they're sitting there tensed waiting for it. But if it takes 20 seconds, they don't care, because they just sit and relax. And each process is therefore responsible for what is technically called the page replacement policy. However many pages you have in the system, in the process rather, the local controller is allocated. It's its job to sort out what needs to happen. Now, the quota system actually ignores the fact that if you allocate every process that's running a quota or its local controller, you're ignoring the fact that a lot of these pages will be shared between processes, because they're the same pages, like parts of the Edinburgh subsystem. So memory gets underused. And the way you solve that is you overcommit the memory by some percentage. You say, well, okay, we've only got this amount of memory, but we're going to pretend we've got 20% more. And that'll be fine, because they'll overlap and it'll all work. Of course, occasionally you get a deadlock, because it doesn't happen. When you get a deadlock, what the system does is resolve the deadlock by doing something fairly draconian and then tuning it back to a slightly lower overcommit level. And that's fine. Likewise, if the system's not using all the memory efficiently, it will increase the overcommit. This caused a bit of a problem when they first put it in. They put it in at lunchtime one day. That was their normal development time. And the system ran quite well. It ran well all afternoon. They could see a distinct improvement. Came in the next morning, the system was hardly running at all. It was incredibly slow. Because during the night, it said, cool, it's a bit idle, isn't it? We'll overcommit a bit more. Oh, we'll overcommit a bit more. So when it overcommitted by about 3,000%, the system went like a slug and it had to gradually tune itself back. So they put in some limiting and then it was okay. Right, last bit is about the director. The director is a part of every page process, and the diagram will make this clearer. It has its own private data for each process, its own stack, and what that influences all the file system. And also the system calls. The system calls are handled by the director and then passed on to the local controller, which actually implements them. ICL called exceptions contingencies, and so they kept on with that. And all the exception conditions, like you hitting a key or failing to do something, doing something nasty like dividing by zero, all come through there. And also it contains functions for that special process direct. And the directory is where the security border is, basically. It runs at a less privileged level than the local controller, so any problem in the directories is not damaging to the system as a whole, but it's more privileged than the user land. And the direct process is unique because it has no base file. All of the code is inside the director. And the reason for that is that you can then bring up a minimal system running just direct, even when you don't have a disk. And that means you get, well, you have to have a disk but nothing else, no file system. So if you, that's fairly necessary. But it's mainly operator stuff, and as I said, process startup and so on. Now, what the director does is provide system calls, as I said, and the most important system calls are the ones that handle the file system. So these are the system calls which are essentially all you need to handle files. You have connect, which makes your file appear in virtual memory, and you can access it like an array. Disconnect, which does the reverse, and anything that's been modified in memory goes back onto the disk. Create, which just creates a new empty file. Destroy, which destroys a file. And I always like to use long words. The actual command to delete a file is destroy, so you can't type it accidentally. Rename, permit, or change the permissions for a file. And there's some clever things there with permissions, which I can't go into here. But you can do things such as, for example, allow everybody to read a file except one person you really don't like, and that will work. Give file names, just give you the names of all your files. A rather interesting one is offer and accept. Offer says, here is a file, I'm giving it to another user. And you offer it, and it stays where it is, but marked. And then when the user knows about it, because you've told them, they can do accept, and the file is moved to their file space, which is quite nice. It's the sort of thing that you quite often need in reality. But it means you haven't got to open up permissions or anything like that. Only that one user can get it. And the last one is new gen, which is a nice thing, which is what we see, of course, on many systems these days. You can overwrite a file while it's in use with a newer version. Existing users get the old one, new users get the new one, and when everyone stops using the old version, it goes away. Oh, the subsystem, of course, the user part of a process, not very exciting, possibly the weakest part of EMAS because its user interface was quite dated. And the Edinburgh subsystem was the one that everyone used. Totally untrusted, mostly accessed by an interactive terminal, and there's a batch command language if you really want to use batch, but we very rarely used it. It's a single process model. When you run a program, it doesn't start a new process like it does in Unix. It's all running the same thing. And you can install your own commands, of course. So typical commands here for the subsystem: analyze, which will tell you about a file, no matter what it is. It's an object file that will tell you about all the dirty details. If it's a text file, it just tells you its size, and so on. Alias, so you have an alias for a command. Of course, people alias destroy to something else and then wish they hadn't. Archive would queue a file for archiving, and the archiver ran once a week and will remove a file from disk and put it on tape. Obey, which is just running a command script. Files, to which what files there are. Edit, edits a file. Lots of different editors you can set up, and they all have different names. Copy, copies a file very simply, unlike VMBK. Option would set lots of options in your process for yourself. One of the interesting ones was cherish. To cherish a file meant you were saying that you really care about this file, and therefore it will get backed up. If you don't cherish a file, it doesn't get backed up. And of course, people get burnt by that. Everyone got burnt at least once. The other thing is that if you have a file that you don't use for 4 weeks, that file will get archived, but only if it's cherished. If it's not, it just gets deleted. People learn that the hard way too. But so many people, they found in the university environment, would actually create lots of files and then go away on a year's research trip or something. And they would leave all these files lying around. And you can't afford that when disk space is relatively expensive. So that was a necessary part of the system. And then there were all these commands below, basically have an analog in the director's system call. Now, as I said, files are just arrays of bytes. I know people who use Unix say, well, Unix is just a stream of bytes, and you don't have any file types. But of course you do sometimes. There are magic numbers at the fronts of files and all sorts. And much like that, the subsystem in Edinburgh has a minimum amount of information at the front, and there's a convention there. You don't have to use it. First 32 bytes tell you about things like its logical size, how much of the file is actually used. It might have a record structure because some people need that, and so on, date and time. And there are things called partition files, which was a hangover from IBM. We can have one big file that contains lots of small files, and you can access them individually from a program for reading. You can't for writing. And you can create subdirectories as well. So I'm now going to show you the system structure, and hopefully this will make it a bit clearer what actually happened before I go on to the last part, which is possibly more interesting. So at the bottom there, you have those global controller. This is your system kernel, if you like, all the device drivers, all the processes that are not paged. And above that, you have a whole series of local controllers, one for each process. And on the left there is a special local controller called the communications controller. I'll come back to that. And that is essentially, there can be many, many processes, typically 100 or something. But there's a dividing line there because the bit below that line is non-paged. It's part of the operating system and it's permanently in memory. The bit above that line is the data for each local controller, and that obviously is paged because the process might not be doing much for ages, so it gets paged out. And collectively, that part of the system is called the supervisor. Above that, you have the director. Every process has mapped into it the director, which again is all paged. And there's one of those for each of the processes, except the communication control, which is very special. And then we have above that the processes, code and data, which is probably the Edinburgh subsystem. It doesn't have to be. And Director 1 is the direct process, and that doesn't have a base file, so it doesn't have that. So the user processes are there as well. It's all paged. And the nice thing about having all the system processes paged like that is you can make them a bit bigger and have more functionality in them. The spooler, for example, had a massive array of messages, which was how we were able to tell the engineer that the fuse had blown, because the guy who wrote the spooler got bored one Friday afternoon and decided he was going to go through all the bits in the status words that came back from the printer and do a message for every one. And it wouldn't take up much memory because all those things would get paged out, so who cares? And just to emphasize that direct has no base file. Communication controller is a special thing. It works a bit like the local controller. It has its own page allocation, which is permanent. It's got no base file, no director, and that's how it does input-output for the network and everywhere else. What happens is that if you want to, for example, print something to a printer, the spooler will hand over the address of a file in its virtual memory to the communications controller, and it will map it and then just do its own work. Very little interaction from the spooler. And that even works for terminals. A terminal has two buffers, which are one for input, one for output. And those buffers are actually part of a file. Everything has to be in a file. The only way you can make memory is a file. If you're a programmer and you want to do the equivalent of a Unix malloc to allocate memory, you create a file and map it into memory. Got some more space. Right, now I'm going to go on to the system from the outside. The initial program load, which is what IBM called it, and it's sort of stuck, or IPL, and ICL called it that too. We call it booting these days. The boot program on EMAS is very large. It's about, I think, what was it, 80K or something, quite big for a boot program. And it contains the device drivers and code to interrogate the hardware. And this is known as the General Reconnaissance of Peripheral Equipment, or GROPE. In fact, there's even a routine inside there called Feel For, which is quite amazing. And it's basically a global controller with a lot of the stuff chopped out of it, things you don't need. So it's a chopped version of the supervisor. And it's called ChopSupi. Terrible. And ChopSupi is a very clever program. It will, when it loads, it interrogates every part of the system to find out what's there, and then builds all the stuff that's necessary for the real system when it loads. And hardware loads ChopSupi. ChopSupi's got all the stuff that tell it how it's going to start, and the register settings are loaded into working register. Off it goes. It asks the OCPs, what sort of OCP are you? Are you 2960, 2970, 2980? It asks the store controllers, SMACs, for memory setup. Memory doesn't have to be in one lump. It asks the store access controllers, which are peripheral controllers, what controllers have you got attached to you on your trunks? And then it asks the controllers, like the disk controller, what sort of disks you've got, how big are they? And ChopSupi contains a lot more. It contains stuff for formatting a disk. And you can transfer an operating system from tape and then load the actual system. That's how you install it. You load ChopSupi from tape, you tell it to, you copy the tape to the disk, and then you start it from the disk. I'll talk about a bit more of that later on. But that really is essentially my rather technical finish to talk about EMAS, apart from one thing. So this is the one more thing. You will recognise that, I'm sure. If you wanted to resurrect EMAS, and I actually started thinking about this back in the late 1980s, perhaps I'd run it on something like a PS2 because it's well documented hardware. You need the source code. So There are no binaries available of anything to do with EMAS because they didn't survive the multiple systems it's been through. My source code of EMAS went from EMAS to VAX VMS to a 5¼ inch floppy or two, and from there to 3½ inch floppies, and from there to bigger hard disks, and so on. So the source of the original EMAS, EMAS 1, is no longer there. You can't get it. You know, it's disappeared into the ether. Source of EMAS 2900, I've got nearly everything. All I'm missing are an assembler, because you remember our assembler was a binary from VMEK, and it didn't survive, and the source of the tape boot block, which I needed. So that's the only thing that's missing. Source of EMAS 3 is patchy. I've got some of it because I did some development. That's all. So if you wanted to resurrect EMAS today, we'd have to use EMAS 2900 as a base. There'll be no other way of doing it. But it will be fun. So that's the easy part. Got the source code pretty well. You need an assembler. The assembler's binary. There's no source code to the EMAS assembler. In fact, I don't even know that it still exists because as soon as we produced the one from VMEK, everyone started using that. So there is no assembler written for EMAS. You've got to use that to build the tape boot block. You've got to use it to build the bootstrap, which is about 600 lines of assembler. There are no sources available at all. So it's possible but impractical to hand assemble that. It's quite complicated. I've written an assembler. The assembler is about 4,000 lines of C, and it took me 3 or 4 days. That was the second time I tried. The first time I tried, it took me a week and I got nowhere. You always throw the first one away, don't you? It assembles the bootstrap quite nicely, and it produces the correct code. So we've got an assembler. That's a start, I suppose. You need an IMP compiler, a compiler to compile that language IMP in which EMAS is written. And it had to compile the particular dialect of IMP that is used, IMP80, in which EMAS is written. I've got the source code of that compiler, but it's written in IMP, so I can't build it, can I? It's also a problem because existing compilers are wrong. The 2900 is a big endian machine. If you know what that means, it means the bytes are numbered from the other end of the word to the modern normal convention. It also uses a weird floating point format, which is called the hexadecimal floating point. It's weird. And you'd also need other modules for getting the output. The compiler that I have the source of doesn't have the module to object code output to provide the environment for the compiler to run in, which is normally the subsystem. So it's a big job to try and get that running. I've written a compiler in C. It's about 27,000 lines of C, and it works. It's currently got a small bug, but that's too bad. I can fix that. But we have an IMP compiler, and it works very nicely. Looks just like the one written in IMP, but it's written in C, and it runs on Unix. We need a linker. Unix people will know about the LD program, which is what the linker is. You build object modules from different bits of source code, and you have to squash them together and connect them. And the linker for EMAS is there, but it's written in IMP. So a bit of a problem there as well. It requires library routines, quite a lot of them, and the compiler environment for EMAS. And it also has heavy dependence on the way it uses files. It has all these files connected in virtual memory and does clever things with them. You could get around that by just reading them all into memory. These days we've got so much memory. I've written a linker. It's only 1,000 lines of C. That didn't take 3 days. It took a lot longer because it's quite complicated. You need utility programs to consolidate object files to make system and process images. There's about 6 different ones in EMAS. One, for example, takes the source code, or it takes the object code of chop suey that's been linked and massages it into a weird form that you need for loading it. The supervisor one has a similar kind of complications. The others aren't so bad. But I've written the one for chop suey, and that means that the one for the supervisor is pretty well done. And I've done all the libraries for creating object file code. So that's not too bad either. So we can produce a binary, or you need binaries of this operating system to resurrect it. but we have no hardware to run it on. I only know one working 2900 in the world, and that's in the National Museum of Computing. So a simulator is the only practical path. And there were two types of 2900. The P series, which were the early ones, the ones that I've been talking about, and the S series, which were the ones with the new Fujitsu chips. And I don't know nearly so much about the S series, but I know a lot about the P series. And the components you need minimum are what's called a SMAC, the Store Multiple Access Controller, the OCP, of course, the CPU with all its instructions, the Store Access Controller, which is basically a sort of direct memory access, a file peripheral controller or disk controller, disks which are normally 100 or 200 megabyte ones, and something called a GPC, which interfaces to things like tape drives and operator stations and printers and so on. So you'd have to simulate all of that if you wanted to run EMAS. Here's the structure you have. You have the SMAC has 4 ports on it, and normally you just connect an OCP to one and a SAC to another. And then the file peripheral controller and the disk go into the SAC. GPC goes into the SAC, and you have a front-end processor who works bits and pieces. And just to make it obvious when you're reading the slides afterwards, if you do, that's how it works. So far it's 35,000 lines of C, that simulator, and it does quite a lot. It does the OCP, it does all the instructions, including floating point and all the rest of it. It supports all the possible P-series machines, including the ones that came later. It does the engineer's panel, enough to make you able to do things that the engineer would have to do. It does a SMAC with configuration options. You can have up to 8 SMACs. The problem is that SMACs can only do up to 2 or 4 megabytes of memory each. So you have to be able to support more than one. You have a SAC, which supports auto configuration, telling you what is connected to each of its trunks, which are the things it plugs into. You have a GPC, which supports auto configuration, but one's enough really. Operator console with keyboard and 2 screens. Haven't tested much of that so far, as you'll see. And a printer, because when EMAS starts up, it immediately starts spewing stuff out on the printer, telling you what's happening in case something's going terribly wrong. So I'm still going to complete the tape drives, which are tricky. The FPC, which isn't, the disk drives, which are easy because they're IBM disk drives. Card reader and punch if I wanted to, and the front-end processor. And then, of course, I'd have to resurrect the operating system that runs on the PDP-11. That's a whole new ball game. But there is a simulator for that, so it's not so bad. What works so far? Well, I've got Chopsy loading and running up to a point. It's actually done quite a lot. I have a compiler error, which is actually due to the big endian problem. It's got 2 words the wrong way around. And I haven't been able to work on it for a while for other reasons. How did I do it? I did it all myself. I started writing a compiler, not for 2900, but for something else in 1989, but mainly in 2021-22. All that COVID stuff, there was a lot of time. In fact, the first part of COVID, I was actually resurrecting a completely different operating system the same way. That's a story for another day. And I started the simulator back in 2002, and then I ran out of time. I think I suddenly got an awful lot of stuff at work. And it's taken a long time, partly because there is very little documentation. The only documentation I've got is 2 partial documents on the OCP instructions, one of which luckily is the design document for the engineers to build the thing. I couldn't source documents on anything else. You can go to the Science Museum and they direct you to their Swindon depot, and the Swindon depot basically it's quite hard to get anything out of them or to get any decent access to the documents. I have some help, and I'm hoping for more, but I've actually managed to do it all so far without. I've done that by reverse engineering the source code of EMAS, which obviously has taken quite a long time. And I'm still doing it. And that really is the end. So I've gone just over time. Conclusion, well, EMAS, relatively long-lived system, 22 years. It was shown to be very reliable. It was extremely efficient at its job, of course. And the university environment is challenging. And I wouldn't pretend that EMAS is a solution for everyone, because it isn't. Not mainstream at all, because university workload is very different. But it proved to be relatively portable. It went from the System 4 to the 2900, to the newer 2900s, to the AMDAL, which had different input-output, and then onto the NAS, which had different input-output again. It was only used in Edinburgh and Kent, and for a little while in Yugoslavia. That's another story as well. I hope one day I'll have it all running again. So for further details, contact me there. I'll leave that up. That's my EMAS website, emas.bobby.uk, and that's on the that'll be on the page for the BTS meeting. And that's really got everything you could possibly want to know, including a link eventually to the video of this. And if you want to look at the source code yourself or documentation, then you can find it there on another of my websites. So I'll leave that up and just really throw it open to questions now, if there are any. Can you unmute everybody, please? Any questions from the floor here first? Yes?
What happens if the system crashed after writing a file to memory?
You're muted.
Yeah, Bob, we lost audio.
Bob, for some reason you're muted, so we can't hear your answers within the room.
Okay, right, we're back now?
Yep.
Yep, okay. Yes, we don't know why I got muted there. I didn't do it. Right, sorry about that. Right, so yes, the last question I have is about what happens if you want to commit the file to disk. The answer is you can only really do that by actually disconnecting it and reconnecting it. But in reality, files get written back really, really quickly. So, anyone else in the room? Yes.
I was interested in your political problems having to buy British.
Yes.
Because Cambridge and my own university actually managed to buy IBM somehow or other.
Yes, I think it was a very narrow window
Yeah.
where the question was about Cambridge managing to buy IBM. I think it was a very narrow window where that wasn't the case.
Yeah.
Right? It might have even been a university thing, you know, high up, but we certainly weren't. It may have been there wasn't enough money in the pot for us. I don't know, but I was always told it was a political problem.
Yeah, we got a 360/44 at St Andrews
Yeah.
in 69, 68, 69.
Well, that time was okay. It was much later on. We're talking about 75.
Yeah,
It was the Wilson government.
white heated technology.
Yes, that's right. Yes, and he managed to get ICL, you know, up and running, as it were, by merging all these companies together. And now it wasn't working all that well, but still, he was trying to sort of kickstart it. Is there anybody out there on the network that would like to ask a question?
Hi, Bob. I was interested in your comments that the EMAS team didn't seem to communicate much between themselves. I only joined in '85, so I think I was the last person to join the team. And I felt the communication in the team was actually very good, especially every coffee morning.
Yeah. Oh, yeah. Coffee mornings were the big thing. Is that Graham, by the way?
Yeah.
Hello, Graham. Long time since I saw you, Graham. What I really meant was that they only knew about their part of the system, and there never seemed to be any time, I think, to communicate between them about other parts of the system. I know when I ended up being in the coffee room, there were a couple of occasions where I said, "Oh, well, you could do it like that," and they said, "I don't know anything about that." And the person whose component it was said, "Well, yes, you can." But I'd been reading all the source code because I was very sad, so it was I was able actually on more than one occasion to be a sort of catalyst, get two of the teams together to say, "Oh, we didn't realise we could do that between us." Yeah, it was more that sort of thing.
Yeah.
But no, I quite agree. The rest of the time we were talking a great deal, and the coffee room was great. I think the lack of coffee rooms these days is terrible.
And the Friday pub.
Yeah. Yeah, it's good to see you anyway. Yes, I knew Graham back in the EMAS days, and he's come today. So anyone else? Yes.
Were there typical workloads and things like that that you would find would run on there that in the university environment? So it was quite different to kind of outside of university environments.
The question is about what kind of workload were the university running, and were they different? I think what we would say there is that the workload in the university, in terms of the batch stuff, would mainly be compiling and running big programs and running them for quite a long time. Relatively little database work, certainly at Kent, compared to anywhere else. And a great deal of interactive work, which was compiling and running programs in Fortran, Algol, BASIC, and C, particularly. But they were never very big programs. So that's the kind of workload there was. A lot of editing and a small amount of transferring files from elsewhere, but that hadn't really caught on at that point.
And a small follow-up then. So you joked earlier about the physicist doing something that made it fall over. Were there specific user groups or people writing workloads for it who would cause you more grief than others?
The physicists mainly would cause the most grief. The question was about who caused the most grief. The physicists seemed to be, they were quite demanding, I suppose, and that's why. But they were quite good-natured about it. You know, some of my best friends as physicists, as they say. Yeah, in this particular case, you know, this guy was not a programmer in a big way, hence the rather buggy program, and he didn't seem to understand the cause and effect he was having. That every time he ran his program, the system crashed, and he would go away for 2 weeks to do another bit of research or something, and we'd all be fine. And then he'd come back and bang. You know. I mean, it happened 3 times in the morning. You know, we couldn't afford that. Well, I think one of the problems with a university workload is that you have to have reliability. Because you will schedule classes for, say, an hour at a time or 2 hours at a time, usually an hour, and the group you scheduled the class for, perhaps 30 people in a room, possibly less, may have come from different departments, but they're all doing the same module. And if the system is down for that hour or part of it, trying to reschedule that across timetabling is incredibly difficult. So you want reliability.
Could I just add to that, Bob? Just I do regarding the use by classes. About a year after I started at Edinburgh, having done a postgrad diploma in Glasgow, I was actually tasked with coming up with a modified subsystem for use by all the Glasgow University first years, because the VME-B system they had there couldn't handle the load. And they actually, for I think 2 years, Glasgow University's first year computing intake were actually using the EMAS system in Edinburgh. Yeah. Also, one other question, you mentioned, you haven't mentioned parallel processing and things like the DAP.
I would love to have mentioned it. I was trying to keep it short. One of the nice things was that ICL produced a rather nice piece of hardware called the distributed array processor. And essentially it looked like a SMAC. So you plugged it in the same way you plugged in a SMAC. It was a piece of memory, but you could do array operations on it. And that was really nice. EMAS was actually modified to handle that. And you could configure a DAP or more than one DAP in, and then run DAP Fortran, which was a special version of the Fortran. Edinburgh produced the Fortran compiler via an associated company. Yeah, the DAP was wonderful because it you could really do a lot of very, very substantial work. But yes, I left it out simply because there wasn't time. Anyone else? Yes.
I'm not sure if this is a question, but I was interested you said that comparing the reliability of the ICL VME machines with IBM. And my experience, I was working.
Sorry, the ICL VME with
2960,
Yeah.
I think it was. It
Yeah.
would be VMEB. I was working at the British Library, in the bibliographic database. Team of about a dozen developers, and some funny front-end machine, Digico, I think it was, don't exist anymore, to handle the multiple international character sets. But anyway, most of the work was done on the VME machine, and that seemed to be pretty good. And soon after that, I worked for Syncom, the American database company that did Total. And I was delighted to be sent to their American office. I thought it was really exciting. Peak of my career was going to be working on IBM. And that was a CMS machine. So you got your own virtual machine.
yeah, yeah.
And that would crash all the time, you know, when it first happened. I said, well, you just re-IPL it, and you just turn that and IBM turn.
Yeah.
And you do that more than once a day, generally. And all we were doing basically was writing programs, mostly in Pascal, and it would just stop, and you reboot it and try it again, and it will work. So a completely different.
Yeah.
But that's, you know, that experience is much.
Well, I mean,
I was at a different level. So
I mean, we weren't involved in at any point in running stuff on IBM operating. The thing was about IBM operating systems and using VMCMS and finding that incredibly unreliable compared to anything else. I've not heard of reliability problems such as VMCMS as usability problems.
well, that was.
You know, it's not a nice system to use. I've used VM, not CMS, but saying that it will crash frequently. Now, for those of you who don't know, VMCMS, essentially, all the system is creates a series of virtual machines which look like an IBM 360 or 370, whatever. And each virtual machine has one user running the same operating system called CMS, Conversational Monitor System, I think. So it's completely isolated, in fact, sometimes too isolated. What Ron was saying was that you would get a crash all the time on those. It's in the 80s, you're saying?
Yeah,
Yeah.
it's 83.
Yeah, I've not heard of problems with CMS. So, but yeah, all you have to do is reboot it, of course, reboot your virtual machine, but it still doesn't give you a very good utilization of your time.
And it was, you know, you reboot it and run the same thing again, it didn't crash.
Yeah.
That was what it was.
Yeah. No, I mean, I haven't heard that. I mean, but there was no point at which Edinburgh, I think, ever ran VMCMS on any of their IBM or IBM-like systems.
Yeah.
They didn't even try it because back in the days of the System 4, they were running whatever English Electric had provided, and then it went on from there.
Yeah.
But yes, I mean, my feeling with ICL was that they, when they merged, what was it, English Electric, Elliott Computers, ICT, Marconi and Leo were there as well, weren't they? All of those into one thing made ICL, what Wilson did, was that they ended up with far too many middle managers, and they didn't really get rid of them. And I have to say, certainly some of the ones I've dealt with were absolutely dreadful. And there's a story I might as well tell you, which I got from a book from the CCS originally, about a manager for ICL who lived in Watford, and there were various places all over the country. One was West Gorton, and in Manchester, and he used to have to go there quite frequently. They'd inherited all these places from different parts of the company. I mean, Elliott were in Stevenage and so on, you know, so he had to go to a one-day conference in West Gorton. So he hopped on the train from Watford, went up to West Gorton, and sorry, I've spoiled the story. Let's start again. He had to go to this conference, so he went to the conference, arrived there. did his day's work, and then came out with a colleague. And the colleague said to him as they were walking out, you know, would you like a lift back? And he said, well, that's very nice, you know, it'd be quicker and all the rest of it. So he got in his car and drove back, and his colleague dropped him outside his house. And he walked into the house, and his wife jumps a bit. She said, oh, you're early, dear. He said, yeah, it's good, isn't it? And she said, I didn't hear the car. He said, car? Oh, shit. And yes, the car was still back in West Gorton. And I suppose that sort of summed up, I thought, the quality of some of the managers. I mean, there were good ones too. But what happened to VMEK in the end, by the way, was that 2 or 3 years later, there was a lot of internal politics, and ICL were really running out of money. And they just dumped the entire project. So we'd have been in serious problems around about 1980, 81 anyway. We would either have had to be given a much bigger machine. Well, I don't know what we'd have done actually. ICL would have had to do something, but it would have meant a much bigger machine. I'm not sure we could have even fitted that in our machine room until they produced the new ones, which were a lot smaller. Yeah. Anyone else? Yeah.
I think what you were saying that, I mean, if I'm not mistaken, without you, this operating system would essentially just go extinct.
Well, Kent it would have done, but then somebody else would have done it instead of me. It just so happened, I was in a rather peculiar position at the time. I had, and it was probably a godsend to them, and actually because I'm interested in that stuff, that's fine. I spent my entire undergraduate career at Kent hacking the operating system and actually subverting it completely at times. And if you look on my webpage, the EMAS thing will lead you to a thing on the left-hand side called anecdotes. And if you look there, you'll see how naughty I was. And one of the things I did when I then became a postgrad and did more things like that and got away with it. The system software manager always suspected it was me and one other guy, the guy who wrote the disk transfer software actually. Always suspected it was one or other of us, but mainly me. And I eventually ran out of money, and I had to do a part-time job, and so I became a programmer there as well. And the programmer part was, you know, the point at which I started using VMEK and sending in all those bug reports. So, in about March 1978, I was approached by the director of the computing laboratory, who said to me, and I was due to finish that September. He said, "There's a lectureship going here. You'd be a fool not to apply for it." You know, so I applied, and there was one other guy, but there's no way he was going to take the job. He was a first-class Cambridge graduate, and he'd get a much better job elsewhere. And so I got the job, and I was due to start in 1st of October. So just after that, they said, "Oh, this guy is coming down with EMAS, and you're the person who knows about operating systems, and you're living on campus, so you're the ideal person." So I got roped in to do it, and so it was all a bit of a coincidence, really, that actually happened. So if it hadn't been me, I guess they would have got somebody else, and we'd probably have done much the same thing. But I was fairly obsessive, I have to say, but I really enjoyed what I was doing, so it didn't matter. A little postscript, which is nothing to do with this really at all, but around 2002, a large chunk of the original staff, 5 of them, all left in one go. And by that time, I was master of one of the colleges, and so I organised a farewell dinner for them all. And lots of people came back, including the guy who had been the senior software manager and my boss. And he said to me, you know, "Hello, Bob, what are you doing now?" I said, "Well, I work here, I teach." "Oh, what do you teach?" he said. And I said, "Well, operating systems." He said, "Why am I not surprised?" Very dry sense of humour, that guy, but it was good. So, right, I think we better wind it up there. So, thank you everyone for coming, and we have largely, I think, managed to make this work. Whether the recording's working is another matter, but we'll see in a minute. We hope to see you again in September, in October, early October. We have already 4 speakers lined up for 4 meetings in the next season, so hope to see you there. Thank you, everybody.
Thank you.